Okay, so this week, again, I'm sorry that we couldn't be there in person. The car broke down, hopefully is getting repaired. Our kids got sent home from daycare and school, and we are now also not feeling well. So, COVID tests, although Dave had a rapid yesterday, so we do know that it's unlikely that we have anything of importance, but we're going to follow all the rules because we very much believe that's an important thing. So today, Dave is going to talk about fabric and catenary structures. There are very few experts on this in the world. I know more than the average bear, mostly because I sit beside Dave while he does this all the time, and I know just enough to be dangerous. Dave, however, is probably one of the experts in the world on this. So this is a lecture that he has given have you given it at AIA? No, you haven't given it at AIA, but he's given it at for RAIC conventions, OAA, IFAI, which is the fabric structure convention they have every year. They usually get him to give this talk or something similar to it. So I will probably be in this week's video very little, and you might see me running up and downstairs to deal with children as they wake up. So I'll prep things and turn it over to Dave. I wanted to say I haven't even looked at the assignments yet. I'm sure everyone did great, and if I get my stuff together, I'll talk about the project. If not, I'll send you guys an email kind of just outlining where things need to be going forward, because I think at the end of the month is when part 1 of your project is due.
Good morning, everyone. I will be, right after this lecture, I will be going for my audition as ranch hand on Yellowstone, but for now I'll do this. I'm going to talk to you about fabric structures today. As Shannon mentioned, this is something that is dear to me. I've done lots of them. They're very fun. They're extremely structurally expressive, which I enjoy, and they're structurally challenging, technically challenging, which I also enjoy. There we are. So, a little bit of background. Fabric structures have been around as long as structures have been around. Some of the earliest structures in the built world were fabric structures. This is a traditional nomadic tent, and we can see forms that look very much like this in structures today. So this would have been a scrim or a weave of animal fur, goat fur, I believe. The traditional yurt, so this is a different type of structure, whereas the nomadic tent, with its distinct sort of peak shape, was a true tensile structure. The yurt uses the fabric to wrap around a frame, which is another strategy that we use today. Another example of a traditional Mongolian yurt, fabric wrapped over frame, so the fabric is the envelope, not the structure in this particular case. Traditional teepee structure, so this is sort of a hybrid in between. This is a little more tensile. The fabric is doing a little more work spanning between the poles, but in many ways it's still a frame structure. And a traditional grass wigwam. So in a way, this is not a true fabric because the grass is not pre-woven. This particular style of wigwam uses bark as opposed to a fabric. Example from the Roman Colosseum, 70 AD. Now some of you who are astute might be saying, Dave, this is not a fabric structure, this is a stone masonry structure. You guys are playing with us. But there is evidence that the velarium had a retractable fabric roof on a rope net. And in fact, if you see the strategy in this illustration, the one that they have found evidence that existed, you can see that this is very much the strategy used for many retractable roof stadiums today, including the BC Place Stadium. The Romans were using military tents in antiquity as well. And the traditional circus tent, which has been around for 150 years or something, has really not changed in a significant way. This is a very familiar form to us. So the first known use was, oh, I said 250 years. First known use was 1770. Common use in Europe in the 18th. I've got to put my glasses on. I can't even read my own slide. Shannon pointed out my glasses are very shiny today. Common use in North America beginning in 1867. 1858, Jeffrey Rhodes developed the field hospital and field hospital tent. And this, again, we can see is an extremely familiar form to us today in agricultural tents. Vladimir Shukov developed this cable net structure in Nizhny Novgorod in 1896. He's really one of the extraordinary, brilliant structural engineers in the world. You can see the tent structure. When Shannon and I were in Moscow, there is an existing tower, communication tower that he designed that is really also just extraordinary. Their conservation groups are fighting to preserve it currently. This one, of course, doesn't exist anymore. And these, of course, are modern military tents, in very common use. F.W. Lanchester developed the air tent in 1919. So this also looks familiar. This looks very much like our soccer domes or golf domes that you'll see. Cable reinforced. The very large ones are cable reinforced today. Some of them, we have much stronger fabrics than they had back then. And so smaller tents are not cable reinforced. But the original air tent was cable reinforced. So this is an air-supported structure, distinct from an air-inflated structure, and I'll try and draw the distinction later. But an air-supported structure, you are occupying the pressurized volume, versus an air-inflated structure, which has inflated cells. This is the J.S. Dorton Arena, the Parabolium, Raleigh, North Carolina, 1952. It stands up today as an extraordinary piece of modern architecture and an extraordinarily innovative and clever structural solution. I'm going to roll it back here. What we can see is this potato chip shaped roof here. It's concave in this direction, convex in this direction. We'll talk about what the meaning of that in a little bit. And it's supported on, oh my goodness, I'm losing control here. It's supported on declined arches. And when I say declined, I distinguish declined from something that would otherwise be vertical, that is at an angle relative to the vertical axis. So declination is the angle relative to the vertical axis, to distinguish it from something that is inclined, which is angle relative to the horizontal axis or horizontal plane. So I refer to these as declined arches because the arch would normally be vertical, and these are declined off the vertical plane. So we've got a declined arch. We have fabric, which is pulling. So the fabric, which is pulling laterally like this. You can see that the fabric, it's actually not fabric, but it's a cable roof. But the tensile roof pulling like this would try to stand the arch up. So the load of the roof is trying to make the arch stand up. That's being resisted by the vertical tension elements in the window mullions. And this is a view from the inside. You can see the cables in the roof. I'm going to pause here just for 1 second. So the Ray Dome. Walter Bird founded Bird Air in 1956 and developed the Ray Dome. The Ray Dome was an an air-supported structure that uses the tensile strength of the fabric. This was his innovation. So where the Lancaster air tent used cables as the primary structural element, the Ray Dome used the strength of the fabric. It was developed after the Second World War, when they recognized that radar was such a strategically important weapon or tool in the fight against during the Cold War. The Ray Dome was developed because it is invisible to radar, because it has no cables or anything. It's invisible to radar, but the radar can be inside it and protected from the elements, from the snow and from all the elements, from snow, from wind, and from rain. In 1957, also, Fry Otto established the Center for Lightweight Construction, which later became the Institute for Lightweight Structures. And Fry Otto certainly did more for tensile and fabric structures than any other individual in history. Some other milestones. 1872, Strohmeyer & Company established for the manufacture of circus tents. 1950s, development of Teflon-coated fiberglass by John Cook at ChemFab, with guidance from Walter Bird. Teflon-coated fiberglass is one of the most prevalent fabric for significant structures today. So Teflon-coated fiberglass, we refer to it as Ptfe. And it is a non-combustible fabric, so it's used in stadium roofs and other large buildings. 1960s was with the introduction of nonlinear finite element analysis, which certainly that's what enables our work. 57, as I mentioned, Fry Otto established the Center for Lightweight Construction. 1960s, Donato Fraioli of Air Structures pioneers air-supported structures for commercial recreation use. So where Walter Bird developed it for military use, it was Donato Fraioli that really invented the air dome, and we're working with his grandson today on some projects, still in the same business. In the 1970s and 80s, the world recession and some notable failures and deflations cooled the market for fabric structures. So we can see that they're not highly prevalent now as they were in the 60s, 70s, and 80s, but I believe that they are making a resurgence. So let's talk about some fabrics. First off, a fabric consists of like shirt fabric or any other fabric. It consists of a weave or a knit of fiber, and it's the weave or knit. It's these fibers that do the work, that make it strong. We primarily work with woven fibers, but knit fiber fabrics are used in structures as well. People have been weaving since antiquity. So this is an image, of course, of an Egyptian hieroglyph showing weaving and dyeing of fabrics. There are many different weaves. The plain weave is the one that we can all imagine, that we've been weaving plain weave since kindergarten, I'm sure. But there are many other types as well, just depending on how many threads get skipped in each at each pass. So this is an example of a loom. You can see that the fabric gets split, and then a shuttle passes through. We have two directions in our fabric. The warp are these threads here. These are the long direction in a way. The warp direction, the warp fabrics, are taut during the weave, whereas the weft directions, the one that goes back and forth, are less taut. So fabric is orthotropic, means that its properties are not the same in both directions. It's stiffer and stronger typically in the warp direction, and weaker and less stiff in the weft direction. Although they're very close. I mean, the fabric weaving has is a very sophisticated project. It's not quite like this.
Kid woke up. I'm going upstairs.
Okay. We often refer to this as warp and fill as opposed to warp and weft, but they really mean the same thing. PVC is probably the most common type of fabric. It's vinyl coated polyester. So the scrim is made from polyester. Polyester is an extremely strong polymer fiber that gets woven into a cloth, and the cloth gets coated then with vinyl. It's very economical. It's translucent. This is an example. You can see the translucency. It's interesting. This, you know, if your intuition would say, oh, that's 50% translucent. In bright sunlight, there's an awful lot of light comes through. This translucency is probably in the 10% range. It's fire resistant, but not non-combustible. So it is a polymer. All polymers are combustible, but they can be coated to manage flame spread. It's flexible, but it's not as flexible as you would think. So it's at a large scale, you can see it can be bent into complex forms. But if you pick up a piece, it's like stiff cardboard. PVC can be colored. It can be printed on, or it can have integral color in it. And it has a design life of about 15 years, which means a replacement life of probably 30 years. So the fabric structures at Ontario Place were only decommissioned 5 years ago or something, and they were built in the 70s. So it's quite a long life, but and comparable to roofing, for example. Ptfe is Teflon coated glass fiber. So it's fiberglass, just like fiberglass you'd find if you're making a canoe or something. You know, the fiberglass structures that we tend to think about would be a fiberglass scrim, a fiberglass cloth, which would then have epoxy or urethane on them and make something rigid. With Ptfe, it's coated in Teflon, so the Teflon is very flexible, and so the fabric can remain very flexible. It's non-combustible. It's got a high light transmission. I think the light transmission, where PVC is in the 10% range, Ptfe might be twice that. Long life, 25 or more years service life, which could be a 50-year replacement life. It's white. It only comes in white. So the Teflon is so smooth that it can't be printed. There's no, you can't adhere a coating to it. So it only comes in white. The benefit of that, aside from the fact that white is a nice color anyway, so why would you do anything else? But the white the smoothness makes it self-cleaning, so it can't. It's almost unstainable. Just when the dirt will simply rinse off in the rain. Etfe. We're working on some Etfe projects right now. Etfe is a foil as opposed to a fabric, which means that where a fabric depends on the strength of the fiber being woven into a cloth, which now has two-way strength, and then coated, a foil is just a uniform polymer. That's it. It's like cling wrap or something, but it's thick and it's very strong. So this is the water cube from the Beijing Olympics. This is the first time that Etfe came into very prevalent exposure, or maybe one of the first times. What we can see is that the facade is cellular. It's broken down into cells of, these might be 6 meters or something across. And you can see that they are all concave. They're all bowed out. Etfe, like so many of these structural forms, is form active. It relies on curvature to be strong. So straight, it's not that it doesn't have some strength if it's purely flat, but it has dramatically more strength when it's curved. And so with Etfe, it's much less strong than the woven fabrics, which means that it needs much more curvature, much tighter curvature to withstand the same amount of load. Because the load demands on this are the same, right? It's snow and wind, just like every other structure. So it needs a much tighter curvature. And so the way they achieve that in Etfe is to inflate it into pillows. So we're seeing the outer foil here. There would be at least one other foil, the inner foil, to make a pillow, and then often there's a third foil in the middle. So low strength and stiffness, very high light transmission. The project that we're doing with Etfe we're using because there was higher light transmission than glass. It's not clear in the sense that there is some amount of light diffusion, but it lets almost all of the light through. It's combustible. It's a polymer. It is combustible, but it's fire safe. So what does that mean? Well, the danger of burning polymers is that they form globs of burning plastic, which then fall, and then it becomes an incendiary. It can set things on fire within the structure. When Etfe burns, the foil is stretched taut. You ignite it, and it pulls away. As long as it burns, it just voids the opening and pulls to the boundaries, and it doesn't drop globs of incendiary burning polymer. It also will not sustain combustion. So if there is a flame on Etfe, it'll burn. But as soon as that flame goes away, it stops burning. So it's not sustaining combustion on its own. At least exposed, it doesn't sustain combustion when just exposed to openness on the other side. Like almost anything, like wood, if you crumple it up so that it can re-radiate within a crumpled piece, I expect that it would sustain combustion, but that's not the way we use it anyway. We use it stretched across a void. Ptfe. Ptfe is Teflon coated Teflon fiber. So like Ptfe, which is Teflon coated glass fiber, Ptfe, the fiber is actually Teflon as well. This makes it extremely flexible, and because it's so flexible, it can be crumpled up and then pulled out again without damage. Most fabrics, as I mentioned, have a stiffness similar to cardboard, which means that if you crumple them up and then you open them up again, there's permanent deformation, which comes from actual breaking of fibers. So we work very hard not to fold fabrics when they're being packed, to avoid folds, whereas Ptfe can be packed, which is why we use it for deployable structures like stadium roofs. The one manufacturer of Ptfe went by the trade name Tenara. They're no longer manufacturing it, is my understanding. So this is a product that may be off the marketplace, but it is so useful and so unique in the marketplace that I can only imagine somebody will start manufacturing it again. SIPE is silicone coated fiberglass. It's flexible. It's recyclable, and it's fire resistant, similar to Ptfe. I've never used SIPE. One of the challenges with fabrics is that because it's two different materials and they are so integral to each other, the coating and the fabric scrim and the cloth, it's very, very difficult to separate them. But in order to recycle them, you need to separate them into their constituent parts. Silicone coated fiberglass, they've just got a much easier way of separating the silicone from the fiberglass, which makes it recyclable. There are companies now that are recycling PVC, so there are processes in place now that to recycle the material, but it's really not in common use. When you tear down an air dome, you're not gonna, or a soccer dome, you're probably not gonna ship the fabric over to Italy to separate and recycle it, which is the only place in the world it's being done. HDPE is shade cloth, very economical, can be colored. It's not waterproof. This is a knit. It's not waterproof because it's so flexible that the coatings, if you coat it, the coating won't last. It'll break down too quickly. But it's used for shade. So this is the what you would see for example, shade sails that you commonly see, these big triangles, or stretched over the frame and at your Loblaws garden center or something. So for tensile fabric structures, the most of this really came out of soap film experiments that Fry Otto started doing in the late 50s and 1960s. And you can see the types of forms that he was experimenting with. So hyperbolic paraboloid forms and these sort of umbrella forms as well, or cone forms. And he also experimented with soap bubbles. So I'm going to come back to this when I talk about the technology, because the way a soap bubble behaves and the way a cone or hyperbolic paraboloid behave are really very, very different, even though it's the same film. And then it was developed. Ideas and techniques were developed using study models. This is a model that my colleague Renee McKay-Lyons built. We did a little workshop in the office where we played with this stuff, and using just absolutely common nylon leggings. We use nylon leggings because they are so flexible. Rigidity makes it very difficult to work with, even though the fabrics that are used in reality for structures are extremely rigid. Working with a rigid fabric is really difficult in terms of developing form finding, whereas if you work with a sufficiently flexible fabric, you can start to see the shapes. Because the study models are done with such flexible fabrics, there becomes a perception that fabric structures use flexible fabrics, but they don't. It's a very, very different behavior. Okay, here's one of the most important things we're going to talk about. Synchlastic versus anticlastic curvature. And this was the distinction between the soap bubble and the hyperbolic paraboloid or the cone shapes. Synchlastic is concave or convex both in both directions. So it might be convex in both directions, like the bubbles that we were seeing. It might be concave in both directions, which would be more like a fruit bag or something. Synchlastic curvature relies on an external source of load to maintain tension in the form. Anticlastic curvature is concave in one direction, convex in the other direction. An anticlastic curvature can be pre-stressed the convex direction, pre-stressed against the concave direction. It's a shame I can't draw diagrams with this format, but I'm going to try this to describe this. We often use two-dimensional analogs to describe three-dimensional structures, and if we want to draw a two-dimensional analog of a synclastic curve, it would be a simple catenary like this. And you can imagine that a simple catenary without any load on it is just hanging under its own self-weight. It maintains a curved shape. but it's very flexible. You go up and touch it, it'll just move around in response to your load. An anticlastic curve, imagine we have a string going down like this, and then we have a second string that goes up like this and goes over that first string. Now we pull the upper string taut, it pulls the lower string taut, and we can pull and pull and pull until those strings break. We just get higher and higher tension in the system. So the anticlastic, it's concave and convex working against each other, which allows us to put pre-stress in the system, and pre-stress makes it rigid. Whereas Synchlastic, you can't pre-stress it. It can only become rigid in the presence of an external load source. So we'll look at this in more detail. What would that external load source be? How could a Synchlastic curve ever be useful? Well, the external load might be air pressure. So when I say external, I'm talking about not within the fabric. So internal to the structure, but not, the load is not within the fabric. So air pressure will apply the external load to a Synchlastic form and make it rigid. We talked about catenaries a little bit last week, and when we were talking about catenaries, I talked about catenary bridges, how they become more rigid when you apply ballast to them. So if we use stone or concrete pavers on a catenary bridge, it's a more rigid bridge than if we have wood pavers or something on it. So or wood decking, which is lighter in weight. So in that case, the ballast is the source of external load that makes it rigid and applies pre-stress. So there's Synchlastic versus Anticlastic. The red being, the two different colors being the convex versus concave. Now let's think about the amount of pre-stress. So this is a form active. So we know that it's highly influenced by the radius of curvature, the amount of curvature. In an anticlastic form, if the radius of curvature is the same, then the stress is the same. So we can generate different, and generally that's our objective. What we try to do is we try to make develop a shape where the stress is uniform. There's a uniform stress field within the membrane. So it doesn't matter which direction you use. Look, it's 10 pounds per linear inch or 10 pounds per linear inch. Doesn't matter which direction you look. In order for that to be true, then the curvature has to be the same in both directions. Now, if we look back at, and I encourage you to do this, Shannon has posted these, so flip through the slides. Go back and look at the soap film experiments that Fry Otto did. Soap film relies on surface tension in the water. That is the tension. The surface tension is uniform. There's no direction to the soap film. So what we know about those soap film experiments is that there's uniform pre-stress in both directions. It has to be in all directions, which means that the radius of curvature has to be the same in all directions. And sure enough, you have never seen an ovoid bubble. A bubble is always purely spherical. When we get into the anticlastic curves in his soap films, you look at those and you can see also they are just like the bubbles. They may be anticlastic, but the curvature is the same in both directions. Characteristic of Synchlastic versus Anticlastic curves is that in a Synchlastic curve we have closed contours. In an Anticlastic curve we have open contours. And one of the things we do when we're designing these structures is we look under load for closed contours. When we load it up and we look at a contour map, if we see a closed contour, that means it's gone slack, and it means that it's formed a trough. which can then accumulate water for ponding. Some other illustrations of synclastic and anticlastic curves. And then there's monoclastic. We didn't talk about that, but a monoclastic curve is one that is curved only in one direction. So a cylinder, for example, would be a monoclastic curve. So I like this element, this image to illustrate the difference between synclastic and anticlastic curves, and to give people an understanding. We get people coming to us saying, I've got this idea of an architectural structure that wants to be cloud-like, and I was thinking fabric, and I point them to this and say, fabric structures are not really tensile fabric structures. They're not so much cloud-like. They're spiky, because the boundaries are, we need to pull out the boundaries in order to get this anticlastic curvature. And if you want something cloud-like, you really have to start thinking about synclastic curves, something that's inflated. Okay, so what's our process? Sorry for flipping through here. What's our process for developing structures? Well, our first step is we have to determine a shape. And the way we do that is we apply boundary conditions. We might choose, let me just see, I had a video in this, and I am not sure if my video works anymore. No. So my video doesn't work anymore. I apologize for that. But what we do, the first thing we do is we determine the shape. We do that by applying boundary conditions. So in this particular example, these four boundaries would be fixed by context. We would determine how much pre-stress we want in our membrane. Our membrane is discretized here. It's broken into a triangular mesh. We determine how much pre-stress we want in our membrane, and that's one constraint. And then the other thing we do is we look at what our boundary catenary is. So tension fabric structures, we've got this tension within the membrane that has to be resisted by something. So with a tension fabric structure, we're just kicking the problem down the field to the boundary conditions. Whereas a beam, you've got tension and compression. You've got compression in the top, tension in the bottom. Tension in the top is balanced by the compression in the bottom. All the forces stay inside, and your supports only carry the weight. In a fabric structure, you've got all this tension within the membrane. We need to resist that by something. We need very strong boundary conditions. The boundary of a fabric structure is often a catenary cable. So we'll put a cable in a cuff, and we'll let the cable follow an arching path. We can put rigid boundaries. We can stretch it against a frame, but very often it's a cable boundary. So our boundary conditions, we would put a fabric in, we would put a cable in, we determine how much force is in the cable, we fix our boundary points, and then we stretch a mesh in between, and it doesn't really matter what the shape of that mesh is that we put in there. We're going to let the computer iterate through this finite element analysis and make subtle changes to the geometry, and then test the forces. Change the geometry, test the forces. And it's going to do this sometimes tens of thousands of times until we wind up with a shape that is in equilibrium, meaning that every node has exactly balanced forces on it, so it's fixed in space. So it's in equilibrium, and all the forces in the primary directions are equal in magnitude. And so that's our shaping. We apply our boundary conditions, our geometric boundary conditions, and our force boundary conditions, and then we tell the computer to go ahead and shape it. This is an example of a cone after a shaping exercise. I really wish I had the videos embedded in here so you can see what the computer is doing. What we did here is we built a model which was a simple pyramid, straight sides. What we know about that is that it is not in equilibrium with a uniform stress field within the fabric. It can't be, because it doesn't have uniform curvature. So we have a flat plane, zero curvature, and then we have a bend, infinite curvature in the bend. So it's not in equilibrium with uniform stress. So then we tell the computer, iterate until you wind up with uniform stress. And what we're hoping is that we're going to get a cone. What we get is this. Up at the top of a cone, you have large radius of curvature, radial, and infinite curvature, or zero radius of curvature, annular. Now, I'll just remind you, because I use these terms a lot, radial along the radius, annular around the circumference. So we have two directions on a circle. We have the radial direction and the annular direction. It's not that you can't apply an orthogonal grid on a circle, but it's generally most useful when you're talking about circular things to think about radial and annular. So in a cone, we have large radius of curvature, radial, very small radius of curvature, annular. They are not equal, which means we do not have constant stress. We have high stress radial, low stress annular. But if we apply a constraint, that way. If we apply a constraint that that we are insisting on uniform stress, then we're going to get a collapse like this. So our model will squeeze it down in like this until it fails. So that's a failed shaping right here. This is a successful shaping. And you see this form in Friotto's experiments. If you take a soap bubble and you touch it with a pin, that soap bubble is going to burst. If you take a soap bubble and you touch it with a big ring, you could push that ring, and as long as the radius of curvature in the radial direction is equal to the radius of curvature of that ring, it's not going to burst. As soon as you try and force it into a geometry where they are not equal, then it will burst. So what we can see is the annular radius of curvature here in red and the radial radius of curvature here in blue, and those are equal at any given point. And so this is a form that's in equilibrium. Once we've got that, we apply our external loads, and we run an analysis. And so when we run the analysis, the computer will apply external loads on top of that internal pre-stress, and again iterate until it's in equilibrium, until every node has equal forces coming off it. And that's the definition of equilibrium, and then we know what the stresses are. So here is our stress plot under just pre-stress, and you say, well, Dave, it's not uniform pre-stress. Look at all those colors. But in fact, you can see that there is very little variation. It ranges from 10 to 10.5, 10 to 10.5 pounds per inch. And the difference is that it is never just pre-stress. We also have gravity acting on this. So there's some weight on this, which means that because there is weight, generally the concave direction will be more highly stressed than the convex direction. And again, we run our analysis. Here's our stress plot. And again, you can see there's very little difference in stress. It's more or less uniform everywhere. Now, I should say that when we apply snow load to this, we load up this membrane, we apply snow load, this is going to change quite a bit. The character isn't going to change all that much. Under snow load, our concave direction is going to increase in load because we're applying a downward load. The convex direction is going to decrease in load. but we never get to the point where we have zero load. If we have zero load in one direction, that means our structure has gone slack. It's no longer rigid. So even under snow load, our convex direction is going to be in tension, some degree of tension. Under wind load, wind generally pulls up. Under wind load, it's the opposite. The concave direction, the tension goes down. Convex direction, the tension goes up. So I've told you that a point is impossible because we have large radius curvature, small radius curvature annular, and yet you see it. It's not uncommon to see it. So how does that work? Well, first of all, our constraint that our stress field be uniform in both directions, we don't have to have a uniform stress field in both directions. So we can have very high pre-stress in the radial direction, very low pre-stress in the annular direction. We tend not to because the forms, well, first of all, our high stress zone, that's going to determine our selection of fabric. And what our general objective is to have our utilization the same everywhere. So that means that our demand capacity ratio, we want our demand to be typically 20% of our capacity everywhere. And then we're using our material to its maximum benefit. In a situation like this, if we have our demand as 25 or 20% of our capacity right up here at the peak, then when we get down here, most of this whole membrane, our demand is at 2% of capacity. And so we're wasting an awful lot of strength. That's one of the reasons why we like to have a uniform stress field, because we can use lighter membranes. The other thing about this is if we come to a point, having higher pre-stress at the point or having higher stress at the point doesn't help you if it gets to infinite. So if you have a zero annular radius of curvature, then you have an infinite radial radius of curvature. If you have a zero annular radius of curvature, then you have infinite stress in the radial direction. So that's an impossible situation, obviously, if we don't have any fabrics with infinite capacity. What that tells us is this is not zero. This might be very small, but it's not zero. So there is some curvature there. And you will see examples of tents where they have what looks like an upside-down salad bowl, just to give it some non-zero radius of curvature in the annular direction, so we don't have infinite stress. And one can imagine that if you took a sharp needle, it would poke through the fabric with no resistance at all. Because instantly, if the needle is sharp enough, instantly the annular radius curvature is zero, therefore the radial is infinite, even with just at a very small scale. And that's true with a syringe in your skin. It's exactly the same. So here's an analysis of our cone shape with a point. And here we can see we have a warp stress. We orient the warp in the radial direction. That's why we're talking about warp stress here. We tend to orient the warp in the radial direction because the radial direction is working harder in a cone. So you can see that where we have 10 pounds per inch of warp stress right at the peak here because it's so high. Look down here, we're damn near zero. So you might say, well, what's the problem? Zero. Like, we got lots of capacity. Obviously, our demand capacity ratio is low. The problem with having these big zones is that they're slack. They're not tight, and so they're going to buffet in the wind. It's a very flexible structure. Without any stiffness, you can get ponding. You get a little bit of you get too much sag, and so water will sit in there. So these are really ineffective structures, which is why they're really only very small. So let me show you some shapes that are anticlastic, just to give you a sense of the range. So this is a simple hyperbolic paraboloid, or a hypar. A hypar is a twisted plane. Take a plane like this, simple square, you twist it, you get a hypar. It's a ruled surface, so straight, 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 twisting. Each one is straight, but they twist on an axis, and you wind up with a warped surface. And you can see a simple hypar, convex in this direction, concave in this direction on the diagonals. So we had a client that was looking for some forms. They wanted to build a simple canopy, and we wanted to give them some ideas. So we went through and just gave them a range of types of forms and structures that they could think about, just to fuel some creative thinking. So this is one that we called a toppled hammock. From a fabric point of view, it's a simple hypar, as you can see. The distinction between this one and the other one is that this one we've only got 2 masts, whereas the other one we had to have 4 masts. We picked up each corner independently. This is a pedal. There's a company called Ide in California that make this as a product. So it's a cowboy hat shaped tube that's been rolled and connected with a membrane stretched in between, and this is a hypar. Now you might think, well, you just told me hypar is 4 points and it's twisted. Well, a hypar really just means anticlastic curvature, same curvature in both directions. One way to generate that is by twisting a rectangular plane. But imagine taking that plane and then cutting with scissors, cutting a potato chip out of it. It's still a hypar. The curvature is still hypar. It's just the boundaries look different. So a pedal is a simple hypar. This is a shape that we refer to as the carousel. So instead of being 4 points, it's 6 points, but it's 6 points, up, down, up, down, up, down. Sort of like Jughead's crown or Charlie Brown's shirt or something. So it's still a hypar. The challenge with some of these, like this one, look at how flat it is in the middle. Flatness can be a problem. You start loading this up, it starts to sag. You wind up with a flat zone in the middle, which is vulnerable to ponding. This is a kite. So once again, the hypar is identical to the other hypars that we were looking at. This is really just about how do you support a hypar on a single mast as opposed to on 4 points of support. And so one way to do it is like this. We take a mast up, 4 struts coming out, and then 4 cables balancing the tension. So we have a strut comes out, strut comes out like this, we have fabric pulling this way, we pull a cable down this way to balance it. This particular client was a coastal community, and they wanted something that was representative of the local culture and the local context. And so we suggested they look at this shape that we called a Manta Ray. Really, all we did, we took a simple hypar and we just cut the end off. We're just going to do a little cut and support it on 2 points instead of 1. And then I stretched out the tail to make it look a little more like a Manta Ray. They really liked this, didn't build it. Here it is from the front. That kite seems to show up every time. This project was in Bermuda. The national bird of Bermuda is I think it's pronounced Keho. So we thought let's look at a structure that derives its form from the wing shape of the Keho. And so we did this. Again, this is a relatively simple hypar. This is just essentially 2 of them stuck together. The national flower of Bermuda is the Bermudiana. And so we looked at what happens if we do something similar to the petal, and we stretch a membrane around this type of boundary. We arrange 6 of them. We put a light up the middle, like the stamen, and we have a canopy that's reminiscent of the Bermudiana flower. And this is the one they chose. It's an umbrella. It's a cone. But it gives them the coverage they want. This canopy, by the way, I don't have a photo of the actual one, but this is, I think, 9 meters across. It's a very large canopy, and it's stood through several hurricanes already. It's right on the water in Bermuda. So these structures are very strong. Look at that. Look at this here. You know, everything else I've shown you, I've been showing you like these smooth curves. Here I've got a cusp in the membrane. If we were in class, I'd be saying, hey, somebody tell me what you think that's about. Well, we're coming up to a point up at the top here, which means that I have infinite radial stress if we come up to a point, or very high radial stress. One way to deal with that is we put a cable in. We put a radial cable, and then we put the membrane in between. And so the cable is doing that high stress. They're taking the high radial stress, not the membrane itself. We can do an inverted umbrella, again a cone. Again, you can see what we've done here is we've suggested that because we're getting very small here, we've suggested a cable. An advantage to the inverted cone is that we deal with water very nicely. A disadvantage to the inverted cone is that the boundaries are up high. So the higher the boundary, the less protection you have in rain. So there's some forms. Now, I have alluded to the fact that fabrics are rigid. And because they are rigid, we can't just stretch them. They don't take the form on their own. We have to make them take their form. And we do this by patterning. And patterning fabric is really very much like developing patterns for a tailor for making clothes. So each individual piece needs to be cut and assembled for something that generates a three-dimensional form. Now, with clothes, we wear clothes loose, and so they can bag, and so they can wrinkle. That's undesirable. We don't want wrinkles in fabric structures. So why don't we want wrinkles? I mean, partly aesthetic, but that's really the secondary. Every time you have a wrinkle, you have an area of high curvature. High curvature, low curvature. High curvature, low curvature means high stress. And so if your fabric wrinkles, good chance it's not going to last long. The other thing is we don't want fabrics loose, because loose fabrics will move a lot, and that movement will shorten the life of the fabric as well. So we don't want fabrics that fit like this pair of jeans, as much as great as they look as a pair of jeans. We want fabrics that look like this pair of jeans. So they've got to be a compound curve without wrinkles. Now, how do they do this? This is not obviously perfectly tailored to her body. This is a flat piece of fabric that is patterned similar to this, and yet somehow it winds up going on unwrinkled. With clothing, they put spandex in the fabrics. Spandex makes it very flexible, and the more flexible it is, the more it can take on complex forms. But our fabrics are not flexible; they're rigid fabrics, so we can't do this. So we need patterns that will do this, which means that we need to pattern the fabric in a way that describes the curve. So here's an example of patterned fabric. We break the fabric down into a whole series of triangles oriented radially. We orient our triangles radially because we want our warp direction to be in the radial direction. The fabric is flat, so it's not going to create a perfect smooth curve, but it gets close enough to that perfect smooth curve that its natural elasticity will pull it into a smooth curve. So this would be tend to be, if this was in space, pre-stressed, it would take exactly, sorry, I keep doing this to you. No, that. It'll take exactly that form, but be slightly faceted because there's no stress. As soon as you stretch it, then it will tend to take the curved form. So we can use computer technique to generate these patterns. Once we know what the 3D geometry is, there's computer programs that will then will put some patterning constraints, and the computer program will generate our patterns for us. And this is what our output looks like. So each one of these is one of those triangular patterns that we saw. Now this file then can be fed into a CNC cutting machine, which cuts them, and then they get assembled. A close-up of a pattern. So the white line here represents the actual exact line from the model. The green line is the cut line. The red line is the match line. So what they do when they assemble this is they overlap until the cut hits the match line, and then they weld that seam. We'll talk about assembly techniques in a bit. The one thing that I didn't talk about yet is compensation. So our final form is a pre-stressed form. So we don't work with the unstressed geometry or the unstressed membrane. We work with the pre-stressed membrane. What happens when you pull on anything is it gets a little bit longer. Everything changes geometry in response to load. So the fabric in our analysis model is pre-stressed. It's been stretched. They're not manufacturing stretched fabric. They're manufacturing unstretched fabric and then stretching it. So we need to tell them, we need to know, how do you have to make this fabric so that when it gets stretched, it takes on the geometry. If we manufacture it to the design geometry, then stretch it, it gets bigger. So what we do is we derive our exact pattern from our analysis model, and we shrink it. So we know that under normal level of pre-stress, PVC will stretch about 1%. So we shrink it 1%, and that way when we manufacture it, it's going to be too small, and we stretch it to its boundary conditions. 1% doesn't seem like an awful lot, but on 10 meters, it's 100 millimeters, and 100 millimeters is not insignificant, and we're dealing with fairly big membranes. And here's that project completed. This is the Sea Lion Sound Amphitheater, St. Louis Zoo. I'm gonna just, so you can see see these radial lines. So those are our fabric seams. So if we have 10% translucency in the fabric, we put two of them one on top of the other, and now we only have 5% translucency. So so the seams show up as slightly darker lines. Look at this big shadow here. What the hell is that? Well, you know that a cone, the stress is higher near the top. The radial stress is higher near the top and less near the bottom. And so what we do, rather than using a fabric everywhere that is strong enough for the load up at the top, in this case we used a doubler. So we used 2 layers of fabric so that we could so that we didn't have to use such heavy fabric everywhere. So 2 layers of fabric when we got up near the cone. The other thing we did here, look at this. This is what we call a Bale Ring. So we don't come up to a point, we come up to a ring, so that the angular curvature is not 0, it's some finite number. There was a very strong reason why the Bale Ring is oriented that way, and I just don't recall what it is off the top of my head. Normally you'd have your Bale Ring oriented normal to the axis of the cone. So you can see that that this cone, the axis of the cone, is declined off the vertical, which would have meant that the Bale Ring would be inclined. But for some reason, the Bale Ring here had to be horizontal, which is fine. I mean, we made it work. Okay, so fabrication. PVC fabrics are welded together using radio frequency waves. Or this is one way to do it. The radio frequency wave melts the coating. So the polyester scrim, the cloth, is unaffected by this. What it does is melts the vinyl coating, and so that the vinyl coating then mixes with the vinyl coating from the other one and becomes one. So you melt and bond and then cool, and you wind up with a good bond. Typical seam is maybe 50 millimeters wide. We can also use heat for welding. So when welding has to be done in the field, they actually use hot air guns. It's a little bit like a hair dryer, but hotter, of course. Another example, heat welding for Ptfe and Etfe. With Ptfe and Etfe, they use a tape and then they heat weld. So they use a tape, which is an adhesive, which holds the thing together, and then the heat actually melts the tape and bonds it. Some fabrics get sewn. So shade cloth, for example, gets sewn. Or boat fabrics, awnings and things. They often use a lighter fabric and they sew them. And certainly early structures were sewn before welding techniques became well developed. Fabrics were sewn. And then here's a silicone adhesive tape which can be used. In Etfe, the foil, it's welded but can also be taped in the field. So imagine, field alterations, field repair for Etfe. It really is like going up with a bit of packing tape and tape over it. So let's look at some assembly details for fabric. Well, this is the very simplest one. Is just a lap joint. So all those those little shadow lines that I showed you, those are lap joints. This would be a ridge detail. So vulnerable areas, we would often put a reinforcing patch. If we had a cable supported, well, let's actually look at this. So this would be a ridge detail. Part of the reason for doing this also is that we really want to shingle the fabric. We don't want, the coatings, the fabrics are really well coated, but as soon as you cut it, you're exposing the end of the cloth, and it can wick water in by capillary action into the fabric. So this is the most vulnerable part of the fabric here, right along the edge. And so what we want to do is we want to the extent possible, we want to shingle the fabric so that the water is always draining across that and down away from it, rather than sitting against it. This is a valley. Valley would be often manufactured with a cable to hold the valley down. So this is an example of a valley with a cable. Look what I told you just a second ago. I told you we don't want water sitting against an edge, and here I've got that detail exactly. So we're always playing the game. It's always a balancing act. The important thing here is we want a reinforcing patch, because the cable will abrade the fabric. And in fact, we have a project where they just had to replace a bunch of fabric because the valley cable actually sawed through the fabric. This is a standard edge detail, which is a cable pocket. So we have a cable running in a cuff, and the cuff wraps around, and this whole thing is welded in here. There's multiple ways of making pockets, but this is a very simple one. This is a corner detail with a membrane plate. So corners are complicated areas where we have a pair of cables coming in, we have membrane coming in, and then they all have to connect back to the structure in some fashion. And it's in areas where the forces are very high. So what we do with membrane plates with corners, we have the end of our cuff. The end of our cuff comes down into a corner. This is what we call a keter edge or a rope edge. So that gets welded onto our fabric and gets bolted down. You can see that we have a rope edge. We bolt that down to our membrane plate. And then the other thing we have a big reinforcing patch. So we know that we've got an area of high stress. We just put a big patch on there and double the strength of the fabric locally. This is an example of a corner membrane plate. A corner membrane plate meaning where it abuts something rigid. So in this particular case, we had a rigid boundary up here. We had a cable on here, and so we get this very complicated condition. It's not obvious here, but what these bolts do is they fix the membrane plate in one direction, but let it slide in the other direction. What we're trying to do here is there's an accumulation of tolerances. The cables are not exactly the right length. The membrane is they're CNC cut, they're CNC printed, but in a way it's a hand assembly and hand welding. They are not perfect. The material properties we're working with are not perfect. So we have test data for the fabric, but it's not exactly right. We've got tolerances in the structural steel, and yet we need this to be a perfect geometry in the end, otherwise it's going to wrinkle. So what we do is every place that anything comes together, we build in adjustment. So this whole membrane plate can be adjusted relative to the structure. It can move in and move back and forth. The cable here has a threaded terminal on the end so that we can pull that cable as well. This is an example of a clamped edge. So if we want to connect to something rigid, this plate here might represent the flange of a wide flange beam, for example. So we have a continuous plate and we clamp it down. And then within this little loop here would be typically a PVC cord. Just a solid piece of PVC plastic about the size of my little finger. So the fabric wraps around it and then you clamp through. This is a gathering plate. So this is a position in the fabric where we have three cables all coming in together. And in this particular case, if it's small, we don't even connect the fabric. It's just a little cutout in the fabric, and the stress will flow around it. But the bigger this is, the more we might need to connect the fabric to this gathering plate as well. This is an interesting detail that comes out of circus tents. This is called a sand pot. So the way the sand pot works is the tent is erected, the mast is pushed up, lifting the peak of the tent until the tent is taut, and then the pot is filled with sand from above. And then the sand is incompressible, so then you lock in the stress in the stress. When you need to dismantle the tent, you let the sand out of the pot, and then the mast will gradually come down. It's not a detail that I've ever used, but I know it exists, and it's used from time to time. This is a more This is a more common condition where we would have our ring and we would have it suspended with turnbuckles, and we would use those turnbuckles to lift the ring and tension the fabric. Our Bale Ring. Typical edge detail with a keter extrusion. So if we have a condition where we can't tolerate the catenary form and we need straight, we would put the membrane into this extrusion here. So again, the membrane comes along, wraps around a PVC cord, and that cord can slide into the extrusion. And the extrusion has these square slots on one side, and a bolt can slip into them, and we can tension the membrane by tightening the bolt. Other types of extrusion, so this would be a lap seam. So this would be a field seam. So if we're making a seam in the shop, then we would weld it. If we need to make a seam in the field, just to break down the size of the membranes, we can use a Kite extrusion like this. This is called an awning extrusion. We can just screw it onto a piece of wood or something else. So some details. This is a cone peak. This is from our project in Kenora. Another example of a cone peak. So again, the membrane has to come up to a Bale Ring, can't come to zero, and then you've got to cover that cone with something, cover the peak. This is the one we did for that project in Bermuda. So we brought it up. It had 4 corners, so we brought it up and we had to make a piece of wood for the top and just ease the edges to round them, just to make it, to give it some softness, not visually, just so we don't have high stresses in the fabric. And then what we did is this very clever detail here that allowed us to lift this fabrication here by tightening these bolts. So you tighten the bolts, you tend to think of pulling something down, but by tightening these bolts, they actually lifted that fabrication. And then we had the top plate on our mast, had these little dog ears in it, which matched, or the teddy bear ears, in a hole, so that they drop this thing on, turn it 10 degrees, put the bolts in. Now they've got this thing sitting up there loose that they can tension from below and lift that peak from underneath. And then we joke that because it's wood, they can go up and they can screw down their rooster weather vane after the fact. Okay, let's talk about light. So this is the available light measured in lux under direct sun, 100,000 lux, clear day 10,000 lux, and overcast day 1,000 lux. It's amazing. Clear day, your light goes up by a factor of 10, whether you're in direct sun or not. With 15% transmission, which is not unreasonable for Ptfe, for example, it's a little higher than most PVCs, and 80% coverage, this is your available interior light. So this is a calculation. 15% times 80% times 100,000 lux. We have 12,000 lux inside, 1,200 on a clear day, 120 on an overcast day. Let's look at what we need. If all we need to do is walk around and we just need to see and not trip over things, we only need 50 to 200 lux. A normal office environment, 200 to 500 lux. A studio environment, 1,000 lux. So you can see that a fabric roof on a clear day, we have enough light for a studio. We've got lots and lots of light, even with only 15% transmission. And we know this. I mean, this is not, if we have a window that covers 15% of our surface area, we know that we don't have to turn lights on. We don't need gigantic windows to be able to function perfectly well inside. Let's talk about water. So what we want to make sure is that there is a positive drainage path to the outside under all conditions. So these are our contours. So you can see based on the contour that the water drains in and down. And that's the critical thing. We always have to manage our water, make sure that we get rid of it. This is the problem. See, when we've got closed contours like this, these closed contours are ponds, and those regions will accumulate water. And the trouble with ponding is you get a little bit of a pond, it accumulates some water. Now you've got extra load, which deflects the pond more. So the pond gets deeper. Now it can take more water. So it gets more water, and there's a feedback loop that happens, and you can actually get ponding instability where it can actually lead to a collapse. That's not generally what happens, but it can damage the membrane. You get actually creep. The membrane will stretch. This is an example of a rain diverter. I actually shouldn't show this one. I should show the other ones. This is an idea I had that we've never actually implemented. This type of rain diverter. A typical rain diverter is a flap of fabric that's held up with something, and often that something is like a pool noodle, or a piece of big old drainage pipe, something. And generally we would put that pool noodle or big old drainage pipe in a sleeve of fabric to match the other fabric. But it's really not very sophisticated. Oh, this is a better example of a diverter with a pool noodle or something inside it. We've occasionally used inflatable diverters, but this is something that is, there is not yet a great solution for how to divert water on a fabric structure. They look nicest if you just let the water drip off, but nobody wants that. Some details. So here you can see we've got a diverter, and this basin at the end where our membrane plates connect to forms a hopper, and then there would be a drain pipe. This is a different condition. So we have our two diverters. We have a dam, and in this case we have a little downspout through the membrane plate, which you can't see. Maybe I've got another image. Yeah, here we are. A little downspout through the membrane plate. And this is really just to direct the water. It's not connected to a drain pipe or anything. There's on the ground below this, there's some riprap, something to prevent erosion. Some cable details. This is called a spelter socket. So cable comes into the socket, it gets what they call broomed out. So cable's all nicely wound, it gets fanned out like a broom. Oh, I thought I had another image here. And then the socket gets pulled so that this is more or less flush with that surface here. This end of the cable's flush with that surface. And then it gets filled with either molten zinc or epoxy. And so it locks it in. What you wind up with is a cone on the end of the cable in a cone-shaped basket inside our spelter socket. These cable ends are swage ends. So swaging is a cold forging. Basically, you get a piece of pipe with a hole in it. The cable's fed into that hole, and it gets squeezed really hard. And it gets squeezed so hard that it bonds with the cable. And that's swaging. That's cold forging. So swaging is generally good for cables up to about 30 millimeters. Above 30 millimeters, we have to go to sockets. How about fire? So all kinds of fire testing on fabrics. Here's the big ones: combustibility and flame spread. So generally, PVC and Teflon have flame spread less than 25, so they're very good in terms of flame spread, but they are combustible. Ptfe is a non-combustible fabric. So if you're in a building that needs to be non-combustible, you've got to be Ptfe. That said, the Canadian building codes have an alternative solutions provision, and we're doing a very large project with Etfe right now, which is combustible, project that needs to be non-combustible, but we were able to demonstrate through an alternative solution that it was fire safe. some structures. This is one of my favorites. This is a very small project, but I love it anyway. This Pearson Park band shell. This is what we call a tensegrity structure. Tensegrity structure means that we have compression elements or struts that are suspended by cable and not connected to the boundary. So the strut is only held in place by those cables and these ones up top. There's a balancing strut here behind that you can just see the shadow of as well. When I talk about fabric being rigid, this is improbable, right? This is a guy that would weigh over 200 pounds, probably walking on the fabric structure, on the one I just showed you, which is not a big structure, and you barely even see a dimple where he's walking. So you can walk on these, you can clear snow, you can wash them, you can do whatever you need to do. What about sound? Fabrics are acoustically reflective. Our intuition is that they should behave well acoustically, but they don't. They are acoustically reflective, and so if we're in a sound-sensitive environment, we need to do some acoustic mitigation. That is the structural fabrics that I'm talking about. There are acoustically absorptive fabrics as well. And those can be installed as an acoustic mediation within a space. But the acoustically absorptive fabrics are not structural fabrics. They're not suitable as envelopes. So it's acoustically reflective, so we need to deal with acoustics if we're in an acoustically sensitive environment. Fabric is like glass. It's a solid all the way through. It has effectively an R value of 0. And so if we need a thermal envelope, we need to build a thermal envelope. There's multiple ways of doing this. This is one example. Bird Air has a proprietary fabric that has 2 layers of PVC with an aerogel insulation in between, and to achieve nominal resistance. We will often see 2 layers of fabric with an airspace in between. So the big the big soccer domes, for example, will often just have 2 layers of fabric and a tempered airspace in between for thermal mitigation. Got to talk a little bit about contracts. 3 ways to do fabric structures: design build, design bid build, design assist. Design build is very traditional, and many projects were done design build because all of the expertise lived with the manufacturer, and so the only way to build them is design build. You let the manufacturer design it because they're the only ones that could. Design bid build is possible, but it's difficult. It's difficult because consultants don't have the expertise. The other thing that's difficult about design bid build is, even if you find a consultant with the expertise, and I think we're the only ones in Canada, there's a small handful in the US, even if you find a consultant with the expertise, the consultant is going to design something that doesn't ideally suit what the successful manufacturer wants to build. So the first thing they do is they throw their hands up in the air, say it's not buildable. You need to change it, because they want to change it to suit their preferred methodology. So design bid build for fabric structures, because they are not commodities, there isn't a well understood and accepted archetype. They're a challenge. That as soon as we go design bid build, we're into conflict right out of the gate. Design assist is ideal. So design assist model, the contractor's on board at the beginning of the design stage to provide feedback during the design and budgeting. At the end of the design, if that contractor is willing to build it for the budget that they help the client set and the client has already agreed to, then they get sole sourced the work. if they can't build it for that budget, then the client can take the project to the streets and it becomes a design bid build. The great benefit of design assist is not that the consultant needs assistance in the design. It's that you get commitment from your builder to your design decisions as you're making them, and so you don't have to go through that early kind of that early conflict stage where they say everything is wrong and needs to change. These structures are extraordinarily strong. So they, our perception of fabric is that they are not as strong as other building materials, but they certainly are. This is a real image of a tornado over a tornado forming over the Denver airport. So this is Denver airport. There's a tornado forming right over top of Denver airport. So very, very, very high wind loads. We did a structure that I mentioned. We've done some structures in Bermuda, and we've designed those for 80, 100 pounds a square foot. Now, just to put it in context, snow load in Toronto is about 20 pounds a square foot. So the wind load on those structures in Bermuda due to hurricanes was 4 times the snow load we're designing buildings for here in Toronto. So all kinds of types of structures. We have tents. We're very familiar with tents, big tents and little tents. So Cirque du Soleil tent, very big one. You can see these are cones, radial fabric. This is PVC fabric, so it can be colored. And using internal masts. See these little peaks in here? Those are internal masts that are used to just create volume. I mean, the volume has to be created to suit the program inside. And rental tents. You see these are flat patterns. It's fine for a very small structure to use flat fabric. It's loose, but it doesn't need to be that tight because it's not spanning very far. Fabric and art. Amazing project by Anish Kapoor called Dismemberment, with a big horn cut through a hillside. Here's a loose fabric. So this is when I talk about Synchlastic fabric, how it's loose. This is a sculpture by Janet Ackelman, and you can see that it's a Synchlastic, it's a bag, and it's very, very loose. That is what she wants. I mean, what these things are extraordinary in the way they move in the wind. Her beautiful sculptures. Fabric for shade. So these are shade sails. Very light, very economical. They are not shelter from a rain point of view. They're really just for shade. This is a stretch tent. So I don't know if you guys are familiar with this, but Eve Lewis has donated a bunch of money to Daniels to do the Belvedere in front, and which is going to be commissioned very, very shortly. And part of that project, which is going to come a little bit later, is a tent, and it'll be a stretch tent. So that it can be a sheltered pavilion during for events. Fabric is used in industrial applications. So this is an interior paint booth or washing booth. This is a fabric portable water tank made by Soapers in Hamilton. Awnings, the Select Bistro on Wellington, Toronto Institution, and awning and other awnings, boat awnings. These are frame structures. So frame structures, they have sufficient structure inside that the fabric doesn't have to span very far, and the demand on the fabric is low. If it doesn't have to span very far, it doesn't need as much shape, which makes it much simpler to fabricate. So this is an airplane hangar. This is a salt storage dome. This is actually a brilliant, you know, you can see the structure is actually really very beautiful for its use. But it's really quite brilliant. It's made of wood. Wood stands up well to salt, which is ideal, although all the hardware is metal. So, but wood isn't damaged by salt. Fabric is a very economical way to cover it, and it's also translucent. And the other nice thing about fabric in a situation like this is that it's a single layer. We don't have deck and membrane and some buildup and then a water shedding surface of some kind. It's a single layer. So if there's a leak, there's nowhere to trap water. If there's a leak, it drips. You know it, and you can go and repair it very easily. And there's nowhere for water to accumulate. I mean, the other thing about being a single layer is that it dries if water gets through it. And so the structure is protected in a way even better than these multi-layer membranes. So this is an ideal structural solution for an outdoor covered rink or something. Oh, look at that, an outdoor covered rink with glue lam with membrane on top of it. I'm feeling a little bit silly because this project has now been built, and I've got photos of the completed structure. But when I prepared this lecture originally, I only had these SketchUp renderings. Eden Project, Grimshaw. I blame the water cube for being first for Etfe, but in fact, Grimshaw's Eden Cube was the first major use of Etfe that I'm aware of. And these were very large. These hexagons, I think, were 9 meters across, very large. And air inflated. Frame supported tent. Air inflated structures. So I just mentioned the Etfe are air inflated structures, meaning that you do not occupy the pressurized environment. There are also air beam structures. So this is literally a balloon, but in this particular case, it's a very high strength fabric under very high air pressure, and they're used for military applications because of fast deployment. Bouncy castle, also air inflated. Cable nets. So this doesn't have a fabric; it just got cable. So this is an aviary in Hong Kong. It's a cable net. Shatir Khan Entertainment Center. Also, this is a cable net supporting an Etfe. So our project in Winnipeg right now is a cable net supporting Etfe. This was the only precedent in the world for that technology, so we went and had a look at it. It's a very impressive structure from a long distance. Up close, it doesn't stand up quite so well, but that seems to be the fairly normal for Kazakhstan. Everything is made for the postage stamp. So these are Etfe pillows. You can see the aluminum extrusions with a clamping plate. These pillows are subdivided fairly frequently. And you can see, interestingly, up close, you can see they get a little bit loose, they get a little bit wrinkly. Ideally, they're not, but there is a little bit of that. Also, from a shallow angle, you can see they're really quite cloudy. But in fact, as I mentioned, they let almost 100% of the light through. They just diffuse it a little bit. Geodesic dome. In a way, this is a spatial structure. In a way, like we need to. In a way, you can't have this conversation without talking about geodesic domes. But in fact, they're not fabric. But these are geodesics that are suspending a fabric, suspending fabric on the inside. And geodesic as a frame structure supporting fabric. Talk about grid shells. So this is an example of a grid shell supporting a single layer Etfe. I mentioned that Etfe is weak and not stiff, comparatively speaking, which means that it needs to be inflated to give it curvature to span. We don't have to inflate Etfe though. It will span a certain distance. It just doesn't span very far. So if we can support it every meter or so, we can do without the inflation. I mean, this is inflated pillows though. You can see the ends here. It's really beautiful. These upstands here are there because the Etfe has dimension to it, right? It's because it's a pillow, it sags in between its support points. So you need to lift it far enough to so that the sag clears anything that it crosses. This is a fabric tensegrity, so these struts just taut within the fabric. I find this one baffling and beautiful. Okay, some cool projects. This is one of ours, Rosebud Veterans Committal Shelter. So this is obviously a teepee, but this is fully engineered for snow and wind loads and 50-year life. Pearson Park bandshell I already mentioned. Some interesting details from that. Sea Lion Sound Amphitheater we talked about. This was our first big one, the Kenora Waterfront Pavilion. This is an interesting lesson. This was originally intended to just be a stage cover. We were not very far down the road when the client came back and realized that it couldn't just be a stage cover. They needed to cover the audience as well. Within a very short period of time, like certainly within the first season, they realized they had so much demand for this venue being right on the waterfront and the space and the amazing space it created inside that they needed a way to enclose the boundary. So they added walls around the perimeter for greater enclosure. And so I'm constantly reminding clients, like, let's just assume in advance that it is going to get used an awful lot more than you expect, and just build in the capacity for that, or have a plan for what to do, because these walls that were added after the fact are really clunky. They're not. In fact, even the composition of the stage cover and the audience cover is kind of clunky because these were late decisions. But the detailing and the fabrication is beautiful. Sorry for the poor resolution of these images. Just to give you a sense of scale. This is at the ridge beam, how everything comes together. This is our project that I mentioned in Bermuda. This is the King Edward Memorial Hospital. This membrane here, which has stood up to several hurricanes, is flat. So there's no shape at all. It's just strong enough that over the 5 meters or so span, it's strong enough to span that. Here's somebody walking around on top of it like it's nothing. This is an arch structure with fabric covering. So this is in Shefferville. We did it in 2013. 100-meter span. So this is a crane inside. You can see a gigantic structure. Competition entry for Centennial Waterfront Pavilion in Sarnia. Would have been beautiful. I'm not sure what happened to that. St. Louis Park Arena, St. Louis Park, Minnesota, or Minneapolis, just outside of Minnesota. And of course, German Pavilion, Expo 67 in Montreal. So this is an absolutely pioneering project. This is, I think, the second big one. The first big one, because the Munich Olympic Park was within a year or so of this. You can see the shapes. So I mentioned the infinite stress at the peak. This was one of Fry Auto's innovations. Is this cable loop? So the membrane doesn't come. I mean, this isn't a membrane anyway. It's a cable net, but it's very similar constraints. The membrane wouldn't come all the way to the peak. The membrane comes up and meets a cable loop. And you can see, if you look at his soap film experiments, you can see where he's developed the cable loop as a means of connecting it. Okay, so here's the Munich Olympic Park, 72. So extraordinary, huge coverage. Cable net with glass, or actually it's a polymer panel, I guess. Giant castings to bring all the cables together. Here's our free body diagram. I don't expect you guys to really look at this. I was just so taken by it. Look at this flying mast out here, suspended from this mast up above. Like, just extraordinary. Ingalls Hockey Rink at Yale University by Eero Saarinen. So this is cables supporting a wood deck, one of my favorite projects, and a gigantic glulam arch. Olympic Stadium in Montreal in 1976. So all these points of support suspended from the tower. The intent was for it to be deployable. These cables would all be drawn up on a big drum here, lifting the big membrane. It never really worked, or never worked properly. Really vulnerable to high stresses. We've got better fabrics now that are more flexible. And so they might have done better now. One of the problems, though, is you get ice buildup on the cables up here, which fall down on the fabric. Yeah, here they are deploying it. Ice buildup falls down on the fabric and damages the fabric. So even they're working on, I think, the third roof now, and that's one of their big challenges, how to deal with that. So that's the last roof, but this one now is being replaced. Atlanta Falcons Georgia Dome, 1992. This is one of my favorite structures because this is an suspension dome. This is a tensegrity structure. So these struts that you can see here are each suspended. Well, let's see if you can tell. The cable coming down here that supports that strut, balanced by a tension ring. Another cable comes down to pick up this strut, balanced by that tension ring. And so we wind up with a tension structure that has a dome shape. And there's the shape from the outside. Here's the free body diagram, or the structural diagram, and cross section. So you can see a cable coming down, supporting a strut, cable coming down, supporting a strut, cable coming down, supporting a strut. And the horizontal component of that force is balanced by this hoop cable. It's just brilliant. The Calgary Saddle Dome. This is an anticlastic cable net. Supporting precast concrete roof. It's Fry Auto's tent in Cologne. No, I guess it's not Fry. Anyway, this is similar to our carousel that I showed you. This is one of the great ambitious Sky Song project. FTL is a architecture engineering company in the U.S., one of the few consultants that actually can design fabric structures, design this. This is the original BC Place Stadium, which looks like the Lancaster Air Tent because that was the same idea. It's a pressurized environment. It's an air-supported structure, meaning that you are occupying the pressurized environment. It was serviceable for, I don't know, 20 years or something, but has since been replaced by this. So the problem with an air-supported structure is that the probability of a deflation event is non-zero. And in a deflation, it's not unsafe, but the roof inverts because it accumulates with snow, and so whatever event you were planning to have gets canceled, and so that becomes a huge liability. And so this is the new BC Place Stadium. You see big masts, what you can't really see is that there are radial catenary cables going across. They all meet in a ring in the middle. And these membranes here on the outside are fixed. They're fixed membranes spanning between these arches. The middle portion here, that membrane is deployable. So that image that I showed you right at the very beginning of fabric all being gathered up, that would be the type of membrane you would have in the middle zone here. So we were the engineers of record for the fixed fabric portion on the outside. Mosaic Stadium Regina. This was intended to be an Etfe structure. This was the concept rendering. And this is basically what was built, which is also a beautiful structure. But this is the Shatir Khan. This is an inside image of it. This is a radial structure, and here's the problem with the radial structure, is that if you orient your cables radially, if you've got something that's got a circular plan, orient your cables radially, obviously they get farther and farther apart the farther away you get from the center, obviously. Etfe will only span about 3 meters. So you can support your Etfe pillow on your radial cables until they get 3 meters apart. And then you need to break them and subdivide them. And then they spread until they get 3 meters apart. You have to break them and subdivide them. And so you can see this happening. There's a pillow. Oh, it has to break here and subdivide. Come down here, it'll break and subdivide again. This just for interest, some of the details. The problem with subdividing it is that you have to inflate all the pillows, which means that you wind up with these clunky ducts running everywhere just to bring the air to the pillows. This is an air inflated structure, the Ontario Celebration Zone by HPA that we helped with. So air inflated structure, of course, you don't occupy the pressurized environment. North York Performing Arts Center. This is interior fabric. All these walls are fabric with LED. And this is the Assiniboine Park Conservatory. This is KPMB Architecture 49. We're the structural engineers for this. This is an early rendering. Just a few weeks ago, they finished putting the Etfe pillows on. So here's a drone shot from above. Like the Shatir Khan project, it's circular in plan. We've got a center focus and radial cables. What we did here, though, is all of our pillows are oriented spirally. So we have our radial cables with spiral cables on top, supporting spiral pillows. This was not a formal decision. It was a pragmatic decision, which is interesting because it has such a formal impact. But the reason we did this is you can see that these pillows, they narrow a little bit, but otherwise they are basically 3 meters wide, the whole length. So we used a constant width pillow, which optimizes the pillow from a material point of view, minimizes the amount of boundary relative to pillow, which minimizes the cost, but also allows us to inflate the pillow only from the top. So we don't have any ductwork anywhere. So it makes the structure much, much cleaner. And here's an image from outside of the structure just a few weeks ago. So the roof is on, curtain wall is going up, and it'll be enclosed before winter, and they'll start their planting program inside. Okay, well, that was fun, very fun for me. I hope you guys found that interesting. And if anybody has any questions about it, we will be in. I mean, hopefully everybody's healthy, and we will be in. We'll see you next week.